Okay. Well, during the lecture, I believe you can always raise your hand or just leave your message in the meeting chat. Okay. Let's start the lecture today. So in this lecture, I will go through the design of the flexible pavement and tell you what's the difference of the new method, which is called the acetone method, how it's different from the conventional empirical method, and how we're going to use the acetone method to complete the design to identify the thickness of each pavement layers. The acetone method is actually very popular for the for most of the pavement design. Well, that of course it's talking about the flexible pavement design. Well, in this lecture, I'll give you a brief introduction about how the acetone method is designed, it's developed, and how we're going to use the method to eventually calculate the thickness based on the traffic loadings, the properties of the subgrade materials, and also the asphalt concrete layers. First of all, for the acetone method, it's actually an extension about the acetone road test in Ottawa, Illinois. It's not Ottawa in Canada. It's this one is conducted in US, and that one was in this method we will consider the pavement serviceability concept for the determination of the thickness of each pavement layers. Well, I will give you more introduction about what is the pavement serviceability. So in the acetone road test, which is the previous version of the acetone method, they were trying to design the flexible pavement based on the repeated traffic load, the pavement design configurations and distress, including the properties of the materials, soils, and asphalt concrete, and the potential distress could be applied to the pavement structure. And the one is the test section is constructed in 1956. It's pretty old in Interstate Highway 80 in Ottawa, Illinois, and it's a very huge project. Cost around more than $27 million in 1956, and the pavement will test the traffic between after the construction between 1958 to 1960, do the measurement about how many truck traffic is applied to the pavement, approximately more than 1 million axle load applied, and it has 74 flexible pavement sections and 49 rigid pavement sections. So this road test provide the instructions for the development of the acetone method with respect to the flexible and rigid pavement design. Here would be the structures about the flexible pavement and rigid pavement for the test road. Basically, for the flexible pavement, it has the surface, base, and subbase layers, and the thickness varies from 20 inches to 25, from 15 inches to 25 inches. For the concrete or the rigid pavement, it only has the concrete layer and the subbase layer. For some design, they don't have any subbase layer. The thickness can vary from 5 inches to 20 inches, depending on the quality of the subgrade or the subgrade soils. So in this lecture, we will focus on the flexible pavement design. So let's go to see what kind of findings from the road test for the flexible pavement. Basically, they find that the design of the flexible pavement, the performance of the road is determined by the subbase materials, the materials of the pavement structures and the subgrade layers. The asphalt treated material has the best performance, followed by the cement treated materials and untreated crushed stone and untreated gravels. Of course, the asphalt treated materials has the cost of that one it's the most expensive, it's the highest one, and the untreated gravel is the easy to be obtained in the field, so it's pretty cheap. For regarding to the distress, we will observe two major distress applied to the flexible pavement, including rotting and the fatigue cracking. And they found that 90% of the rotting occurred in the pavement layers, so they will cause the deformations about the pavement structures. And among all those rottings, 32% are in the surface, approximately 14% in the base layer, and 45% in the subbase layer. And for the fatigue cracking, they were also observed a lot of crackings during the winter time. So the temperature or the freeze thaw effect has a significant impact about the fatigue cracking of the flexible pavement. And the pavement deflection will be greater during the springtime compared with the time in the summertime. I guess this is caused by the freeze thaw effect and the increased moisture contents of the subgrade layers. This is common as what we have analyzed previously about the soil materials, the impact of the moisture contents, and so on. So based on this, based on these findings, the engineers make some summaries from the test, from the road test, and find out some key parameters applied for the flexible pavement design and develop the ASTO 1993 methods. This method is determined based on the pavement serviceability concept. The serviceability is a new concept that we're going to use for the ASTO methods. It's defined as the ability of the pavement to serve its intended function under the existing conditions. So we will try to see how the experience of the users, especially the truck users, about the pavement, whether they feel any a lot of disturbance or I feel that the road is quite smooth or not. In the test, the road users will the pavement is actually based on the response, the survey from the road users. In the test, the road users will provide their rank, their rate about the performance of the pavement, which is called the pavement service rate (PSR), and then based on the pavement, the roughness, how comfortable the truck driver is running on the road. They will be categorized into 5 levels. 0 to 1 means poor, 1 to 2 means 0 to 1 means very poor, 1 to 2 means poor, 2 to 3 is fair, 3 to 4 is good, and 4 to 5 is very good. And we also use the PSR, the pavement serviceability rating, to develop the design equations and predict the present serviceability index, PSI. This is the value we're going to use. And the equation here shows how we're going to calculate the PSI based on the PSR. So in this equation, SV is the average of the variation of the slope and of the profile. So it represents the slope of the road. And RD is the average of the rotting depths. So the how many centimeters of the rotting is applied to the pavement. And P is the area of the hole. What kind of percentage of the road is occupied by the hole. And C is the area of the damaged zone. What's the percentage of the areas which will have some distress. And this one provide the equation to calculate the PSI theoretically. And this is one typical surveying. which will be applied for us to identify the PSI, depending on the response from the road users. And also they will provide the response about whether the pavement is acceptable or not acceptable, or they're not quite sure. So they will also provide the PSR ratings from 0 to 5. And we're going to use this one and the equation here to calibrate these models, this linear equation, and we find out those parameter coefficients. And with that, we can determine the serviceability index theoretically. So the here, that will be a definition of the pavement serviceability, and it plays a very critical role for the design of the flexible pavement. And in the actual method, we have to consider more parameters compared with the other empirical methods, including the design life, which is the durations of the pavement, and it will include the analysis period, which before we design, we want to consider how long we want to do the evaluation about the performance, and also the performance period indicates that the period that the pavement can maintain the serviceability index, pavement serviceability index higher than certain value. Usually the performance period is smaller than analysis period. We can try to do the analysis to see what happens if the pavement reaches to certain PSI less than the terminal PSI values. Of course, we also want to consider the impact of the traffic. This one is quite similar to what we introduced previously. We want to estimate the ESAR for the design period. And we also want to have the condition for the reliability, how reliable the pavement it is during the design period, the environmental effect, the moisture contents, the freeze thaw effect, and so on. The serviceability, which would be the PSI. And we especially want to see how the PSI is changing from the start of the at the end of the construction to the time when the road is not functioning appropriately. And of course, we need to think about the material properties, including the subgrade resilient modulus and the pavement layered materials, the granule base, granule subbase, and the hot mix asphalt. Especially we want to know the MR values. And also we have to know the drainage conditions of the pavement design. So all the factors that we learned in the previous lectures will be combined here for the design of the flexible pavement. And this equation shows the design of the flexible pavement and tells you how the relationship between the designed traffic, which would be W18, is showed the ESAR, the ESAR with the standard load, and it would be a function of the set of variables. ZR is the standard normal deviate. SO is the combined standard error of the traffic and performance prediction. Delta PSI, this is one of the important factor. It's the difference between the initial and the terminal serviceability index. And MR is the resilient modulus, SN is the structural number. This is another important factor we have to think about. It was related to the performance of the flexible pavement. And also, you need to keep in your mind that this equation, all those coefficients, they will be calibrated for the empirical units. So that for the length, it should be the depth, it should be in inches. For the resilient modulus, it should be under the unit of PSI and so on. If we are using the SI unit, then you have to consider changing the coefficients or apply different coefficient values. So that would be the design factors we have to consider for the flexible pavement with the Ashton method. And we also have some typical recommendations about the design period, depending on the conditions of the roads. For example, for the highway, for the urban highway with a high traffic, usually the design period is around 30 to 50 years. But for the rural highway, the design period is shorter. It's only around 20 to 50 years. And for the low traffic urban highway, the design period is 15 to 25 years, and for the low traffic rural highway, it's 10 to 20 years. So this will be some typical analysis periods we have to consider. It's not the actual performance period. Usually, the performance period is shorter than this one. And regarding to the second parameter, that will be the traffic loading. We have introduced the traffic loading a lot. We need to find out the equivalent single axle load, ESAL, and we need to use the load equivalency factor, LEF, to find out the ESAL for the design period. And also we have to consider the length factors, the length distribution factors, and the directional factors, and so on. Usually for the road with only one lane in one direction, then the length distribution factor is definitely 100. If there are two lanes, then the percentage is around 80 to 100%. And if we have more lanes, then the percentage will be smaller, which means that the truck will have more lanes to choose during the designed pavement. So this would be the length factor. It's also important for you to calculate the traffic loadings. And here we have some typical load equivalency factors applied for the flexible pavement. The load equivalency factor is determined based on the axle load and the structure number and the terminal serviceability index. So there will be three parameters: the load, the structure number, and the terminal serviceability index. So for example, for the load, for the gross load with 10 kilopounds, or we say that 44.5 kilonewton, then the under the structure number of 3, terminal serviceability of 2.0, the LEF for the single axle is 0.09, for the tandem axle is 0.008, for the trailing axle is 0.002. And you can also find out the values under different structure number and the terminal serviceability index. So with this table, you can find out the LEF for different axial combinations and the different load with different service, the different structure number and the terminal serviceability index. And we can also find out the another table to show you the LEF for the single axle with the terminal serviceability index of 2.0. With that, you can find out the LEF with different load and the different structural number from 1 to 6. Basically, with a higher structural number, the LEF will be smaller. So the high structure number indicates that it's highly related to the thickness of the pavement layers. Usually with higher structure number, the thickness of the pavement layer would be larger, and that's the reason you observe the smaller load equivalency factor. And this is for the single axle with the terminal serviceability of 2.0. We also have the table for the tandem axle with a PT equal to 2.0. Similarly, you can find out the value under different service structural numbers. And we have another table for the trailing axial with PT equal to 2.0, and you can find out value at different structural numbers. In addition, we have another table to show you the pavement structure number, the LEF under a single axial with a PT of 2.5. So this is something different from the previous one. Of course, you can find out the value with different structure numbers. We also have the table for the tandem axial with PT equal to 2.5 and trailing axial with PT equal to 2.5. So those would be the LEF we're going to use. And again, we have another table for PT equal to 3.0 for the single axial, equal to for the tandem axial and trailing axial. For the homework and the exams, if you are asked to do some to do the ASTO method for the design of the flexible pavement, you will need to go back to refer to those tables to find out the LEF of the different axials and use the value to calculate the ESAL. And this would be the typical worksheet that will be applied for the calculation of the ESAL, assuming that you have the design period of 20 years, and you have the structure number, or say that the if you don't have the assumed structure number, but you have the assumed thickness of the pavement structure, you can then use those information to calculate what's the total ESAL. So basically, you're gonna observe the current traffic for the so this is the first column is observed. You're gonna observe what is the traffic for the passenger car, for the truck, for the bus, for the pickup truck, for the other type of the trucks, and so on. You can find out the traffic for different volumes, and then you can calculate the growth factor. So you are provided with the annual growth rates R equal to 2%, and you know the design period Y equal to 20 years. Then you can calculate the growth factor. Will be, I will not go to the details about the calculation, but that will be 24.3. So that will be the growth factor. And with that, you can find out the design traffic for the design period. That will be the A times B. And you can then find out the ESAL factors, which would be the one you can find from the previous tables. That will be the factors LEF. That will be the LEF you need to check. And with that, the designed ESAL would be C times D, the design traffic during the period times the LEF. So this would be the ESAL for each group of the vehicles on the road, and if you sum them together, you will get the total designed ESAL for the road. So this is the worksheet for you to calculate the ESAL based on the observed data and based on the LEF that you tracked for each type of each group of the vehicles. And that's the second parameter, the traffic. And the third one is the reliability and the standard deviation. This would be some values applied for us to identify how the performance how the performance of the pavement is during the design period, whether it's reliable or whether it's easily be broken due to some overloadings or some changes in the weather conditions. For the ASTO method, we will find out the design reliability and standard deviation based on the type of the road. For example, for the interstate highway or some other busy highways in the urban area, the design reliability is 85 to 99.9, but for the rural area, it's between 80 to 99.9. You can also find out the values for the other type of the road, including the principal arterials on the local roads, the collectors, and the local roads. You can see the reductions about the reliability for the road with less traffic. And for the standard deviation, we will usually choose some typical values for the flexible and the rigid pavement. For the flexible pavement, it's between 0.4 and 0.5. And for the rigid pavement, it's between 0.3 and 0.4. So those would be some data, some values that you can choose from the experience. And you need to specify one value. Generally, with a higher reliability and standard deviation, smaller standard deviation, it indicates that the road is more reliable and can last for a longer time. And we will also have the some typical values about the reliability, relationship between the reliability and the standard deviation. Usually we're going to choose the reliability and the standard deviation from the table here. For example, if the reliability is 50%, then the standard deviation will be set as 0. If the percentage increase to 95%, then the standard deviation could be selected as minus 1.645. Depending on the this would be some typical values you're going to use, depending on the reliability you choose for the pavement, and then you can determine the standard deviation. And now I will go through one example and let you know how we're going to use this one to conduct the design of the to estimate the ESAL with the equation that we just showed. In this example, we are provided with the reliability as 95%, structural number as 5, SO, which would be the standard deviation, as 0.35, resilient modulus as 5,000 psi, and we also know the changes in the pavement serviceability index from the initial to the terminal status. That one will give you the with this information, we can then calculate the ESAL. So in this, by the way, I think I give you the wrong definition about S0. So S0 is actually the combined standard error of the traffic and performance index. This is usually provided. It's different from the standard deviation. So with that, we can first use R, which is 95%, to find out the standard deviation, ZR. We can go back to recall the table here. For 95%, ZR is minus 1.645. And then we can apply the equation log W18 equal to the ZR times S0. S0 is the combined standard error, and plus 9.36 times the log of the structural number plus 1 minus 0.20 plus log delta psi divided by 4.2 minus 1.5 divided by 0.4 plus 1094 divided by SN plus 1 to the power of 5.19, and plus, this is a very long equation, 2.32 log MR minus 8.07. So you know the values of ZR is minus 1.645, S0 is 0.35, Sn is 5, and delta PSI is 1.9, MR is 5,000. So with that, you can get a value of this log W 18 as 6.714, and that one is W18 will equal to 10 to the power 6.714, which would be 5.18 times 10 to the power 6. So that's the way for you to calculate the W18, which would just be ESAL for this specific example. So I will pause here for any questions you have. Do you have any questions about the analysis so far? Okay. If no, I will continue this lecture. So for the design serviceability loss, which will indicate that the difference of the serviceability index at the beginning and the end of the permanent structure, we say that P0 is the initial serviceability index and the PT is the terminal serviceability index. For the rigid pavement, P0 is 4.5, and for the flexible pavement, P0 is 4.2. And for the terminal serviceability, if it's the major road, usually set as 2.5. If it's some minor roads, then we set this one as 2.0. So the pavement serviceability index is usually just between 1 and 5, as what we defined previously. 0 to 1 just indicates that it's very poor, and 5 indicates that it's very good. With the initial and terminal values, we can find out the serviceability loss during the design period. And the values of delta PSI or the loss of the serviceability index can be caused by the traffic conditions or the climate factors. Those should all be included. But we're going to use the delta PSI and assume that delta PSI is only determined by the traffic. So this is one kind of the assumption made by the ASTO method. It's applied to simplify the whole design. So the figure here shows the typical trend about PSI, how the PSI is changing over the time. And at the year 0, you will have the initial PSI, P0, and after several years, you will observe the reductions about the performance serviceability index, and at the design period, it will reach to the PT, which would be the terminal serviceability index. And when the PT is less than the when the serviceability is less than the terminal index, then it will be uncomfortable for the drivers to move on the road. And this is actually based on the survey about the actual driver's experience to the terminal serviceability. The table shows one kind of the survey result. Like a majority of the people think that the when the serviceability index is 2, it feels unacceptable, and some of them think that if it's 2.5, if it's below 2.5, is unacceptable. So we find out the average value and determine the terminal serviceability index. And that's the term serviceability. And the next thing we need to think about is the material property including the properties of the subgrade materials and also the properties of the asphalt concrete. So for the subgrade, let's first go to the subgrade layers. We want to calculate the effective resilient modulus. It's different from the one that you estimated from the lab experiment. But first, let's just a quick review about the resilient modulus. From the MR test, the resilient modulus is determined by the stress and the recoverable strain. So the cyclic stress divided by the recoverable strain will give you the value of the resilient modulus. But in the design of the with the acetone method, we need to adjust the resilient modulus to consider the seasonal impact, because we know that the MR is changing at different moisture contents and temperatures, and we have to do some adjustment for the MR values to consider the impact of the whole year to the pavement design. So with that, let's see how we're going to conduct the adjustment. First of all, we know that the usually for the MR, for the resilient modulus, the value will be high when it reaches to the summertime, and it goes to gets lower when it reaches to some to the winter and or the springtime. So the it just indicates that the values is changing over the time. We cannot use one value that we measured at one specific month for the design of the flexible pavement. Instead, we have to consider the variations of the resilient modulus over the whole year, at least over the 12 months. And to do that, we will introduce a new variable, which is called the UF. The UF, we will first convert the MR, for the MR that we estimated at every month, to the value of UF. And then we're going to find out the average value of the UF and convert it back to the MR. This will give you the adjusted subgrade resilient modulus. Let me give you one example about how we're going to do that. Assuming that we have the measurement about the MR, so this is measured. For every month, in January it's 15,900, February it's 27,300, and you can find out the different values over in each month. And then we're gonna apply the equation UF equal to 1.18 times 10 to the power 18 times MR to the power of minus 2.33 to calculate the UF at each month. For example, for January, we know that MR is 15,900, and it gives you the UF as the 15.900 to the power minus 2.32. That will just give you the value of 0.02, which would be the value of the relative damage UF. And you can find out the UF for different months. And eventually, once you have the relative damage UF for every month, you can then calculate the UF, summarize the UF for the whole year. So if you do the summation, that is 25.3. With that, you can then find out the average damage, relative damage. That is summation 25.3 divided by 12, which will give you the value as 2.11. So this is the average relative damage over the whole year. And then you're going to use the equation. You're going to apply the equation again. 1.18 times 10 to the power of 8 times MR minus 2.32. To find out, we know UF is a 2.11. And then you can use this equation to find out the value of the MR. This is the adjusted. This is the adjusted MR. You can also use, if you want to skip the calculation, you can just use this scale, but directly. For example, for the UF equal to 2.11, if it's 2.11, that will be someplace around here. With that, it gives you the MR value around 20. So UF is 2.11, and on the right side, it gives you the MR. So this is the UF, this is the MR. It gives the MR value about 2.2 to the power 3. So that's 2200 psi. So you can also find out the same value from the from this equation directly. So this is the adjusted MR values, and we will need to use this adjusted value to find out the for the design of the flexible pavement. And then at last, we can go to see the actual design. For the flexible pavement design, it's highly related to the parameter which is called the structural number. The structural number will be related to the performance or to the characters of each layer in the flexible pavement. So this equation shows the structural number. Assuming that you know the structural coefficient AI for each layer, and you know the thickness DI for each layer. For this case, you have D1, D2, and D3. And also you know the MI, which would be the drainage coefficient. With that, you can calculate the structural number as the summation of AI times DI times MI for all the layers. Well, for this specific example, it's A1 times D1 plus A2 times D2 times M2 plus A3 times D3 plus times M3. Usually for the first one, for the asphalt surface layer, the value is 1. So we just skip that, simplify the equation. And so that's the structural number. And we also have some charts for you to identify the structural coefficient which will be related to each layer. For the first layer, for the asphalt layer, we can just recall this equation, recall this chart. Depending on the resilient modulus, we can find out the structure coefficient. If the resilient modulus is 200,000, then the structural coefficient will be 0.3, and you can find out the value of alpha 1 for any values of the elastic modulus. So that's only applied for the asphalt concrete layer. And if you have for the granular base layer, you can then refer this chart to calculate to find out the coefficient. So this line, the line on the right, shows the resilient modulus in thousands. And if you know if you know the resilient modulus as 20,000, you can then go back to find out the value of the CBR and also the coefficient, and this one gives you the value of 0.1 for alpha 2. So this chart is only for the granular base layer. And of course, we have a similar chart for the granular sub-base layer. Depending on the value of the resilient modulus, we can find out the structural coefficient for alpha 3. So if the modulus is I guess here it's if it's a 13.6, then you can find out the alpha 3 will be 0.1. Okay, I guess I will not have enough time to finish this lecture, today, so I will pause it here. And I also plan to have give you a quiz and a very simple question to understand your skills in the stress and strain analysis of pavement. The quiz will be available on Avenue to Learn. Let me just make it alive, and you can have you can work until 2:25 to for that quiz. Okay, I guess I just uploaded yesterday. Do you have the oh, I'm sorry, I forgot the one I have already uploaded here with you. So the so if you have already worked on that quiz, you can just skip it. If you haven't, I will just give you another chance to work on that quiz. I'm sorry, I just totally forgot that I have made it available for you yesterday. So just to make it alive again, and you can work on that if possible. Because I received some requests from the class that they don't have a chance to work on the quiz, and this will be another chance for you to go through it. Okay. In the meanwhile, I would like to take this time to get any questions from you. Do you have any questions about the lecture today and the design of the, especially the design of the flexible pavement? It takes longer time as I expected to go through all the flexible pavement design methods, and we still have plenty of the time to finish all the topics of this class. Just feel free to let me know if you have any questions about it. Okay, if we don't have any questions, I believe that'll be all for the lecture today. And just feel free to send me email if you have any questions, and also if you have any issues about the homework assignment, let me or the TA knows, and we will try to help you to work on that. We have I'll update with you about the details of the final exam so that you will have some schedule to plan for the final exam. Okay, I guess that's all. Thank you very much for your time, and I will see you next week.